And I was on it. The bike ride yesterday was a little bit rough. It seems like Bob might have overslept, which means that we'll just swap our two lectures. So I'll go now, and Bob will go this afternoon. So because I didn't prepare the lecture yet, it means I'll need even more help than usual from you guys. So we'll figure this out as we go along. So what I'm going to talk about, so lecture 2 is Sequin calculus. And there's a subtitle, if you will, which is that in this lecture we'll actually go from this notion of inference to logical connective. So from inference to logical connectives. An interesting aspect of this is that if you know the techniques that we use in proof theory and type theory in order to define logics, the way we actually think about writing down the meaning of the connectives and so on, then everything in linear logic just starts from this very simple seed that we had in the last lecture. Okay, so from now on, basically, there isn't that much flexibility. You don't have that much leeway into how you go about defining things. Okay, so you just say, you just follow the strategy that we know how to follow. Okay. Yeah? Bob, do you want to swap our two lectures, or?
Well, I get up early in order to be here for this.
Okay, sure. Okay, so this was a preview. Okay. At 2 o'clock, I'll tell you about this.
So now for something completely different. All right, where were we? Is there a pen? All right, thanks for stepping in. Sorry I'm late. Oh, I need to put on the device. There it is. Okay. All right. Sorry, switching context. So where we were last time is we had started to get now some real traction because we've introduced the essential ingredients or distinctive ingredients of dependent type theory, which is as we talked about, the generalized or the dependent sum. You could solve this, and we can call this a dependent. The dependent product is more typical, and we began to talk about the identity type, which is written like this. And this is identity, or you could explain it as equality, or as I will explain shortly, it's sort of an abstract type of what are called paths in a space. And so the interesting thing about it that I was mentioning last time that I think is important is that we tend to have both for lack of a better way of describing it, we tend to have both a propositional and maybe, I don't know, what should I say, typical attitude toward, towards this type, the identity type. And this is going to seem unfamiliar to you unless you happen to be somebody who's experienced in type theory. But this will, I'm addressing people who aren't. So I'm going to say that this is going to feel a little odd. Everything I say today is going to be technically delicate, and I'm probably going to screw it up. But I will try not to. And on the technical details, I hope only. And it's going to present a different perspective, I think, on logic and proof than possibly or very likely many of you are used to. So as a matter of notation, by the way, because we so frequently have taken attitude toward this of being a type, a family of types actually technically, but also as a proposition, we have another notation that we'll often use, which is the equal sign with an A here, or sometimes even just not even bothering to write the A, or possibly writing it over here to stress where it belongs. So we'll frequently write this notation. Now this is what is going to confuse you, because what I'm going to say is in fact a valid representation. It is a valid representation of a principle of equality. It is a notion of equality, but it's a notion of equality which exploits very critically the notion of proof relevance, because we're going to think of this as the type of identifications I talked to you before. So we can think of this as the type of identifications, or as I will shortly explain, the idea of paths in a space. So identifications or paths in a type or a space in a type. Okay, that's the way we're going to think about this. So it's a type in some type, in other words, in the type A. So by the propositions as types principle, if there exists an identification of A and B, then we will say A and B are equal. And that's the idea. So A equals B will be true, or we will just say A is equal to B when there exists an identification. So that's in keeping with everything else we have said about propositions as types, the inhabitation expresses this idea of truth. However, in the setting where you're doing proof-relevant mathematics, where the propositions classify their proofs, then the structure of the proofs of a proposition becomes a topic of discourse. So rather than, as usual, speaking about whether a type is provable or a proposition is provable or has a proof or is true, we will also talk about the structure of the space of proofs of that proposition. So we'll have a much more highly refined notion than what we're used to. So in particular, we will find that rather than prove things, so like a usual sort of kind of fact that one might do is might end up saying, well, I'm going to write something schematic here rather than a specific example. We might end up saying, well, a statement like, some sort of A is equal to B if and only if, C is equal to D, or something like this. This kind of thing could come up a lot, so I'll just put that as in quotes, and I want to draw a distinction to something. This would be conventional mathematics, is that we often think about if these are propositions, when we want to say the two propositions are equivalent, we say A if and only if B. So as a matter of fact, there's no reason for me to insist on these being equations. So in typical situation, we'll often prove A if and only if B. All right, that's a very common, or A implies B or B implies A, whatever. But let me just take that as an example because I want to connect it with equality. So a lot of times will happen, a theorem is stated as something, two propositions are equivalent. That's fine. If we render this as propositions as types, what this is saying is that there are maps in either direction, okay? Which is to say there exists an F which transforms any proof of A into a proof of B, and there exists a G which transforms a proof of B into a proof of A. So that's what that means. So when you say if and only if in a conventional setting, when you transpose that into by props as types into type theory, it means there are maps in either direction. But that is a relatively weak idea because we can actually do better. So the sort of modern sort of view, the homotopy type theory view, or the type theoretic view, is to say, well, wherever possible, and frequently it is possible, we're interested not merely in whether everything here could be mapped to something in here or back, but in the nature of the relationship of the structure of the proofs of A to the structure of the proofs of B. And what we'll often end up saying is we will be proving that A and B are an equivalence. So this is called an equivalence of types. And it'll take us a little bit to explain what an equivalence is, but the idea will be, you can think of it as an isomorphism up to isomorphism. That is like a little kind of slogan. So the idea will be that where we're going to get to eventually, and I will get there, we'll get there eventually, is that we're going to have maps back and forth, okay? So we'll have this condition, let me not just write it out. But moreover, we will have reason to believe that these are inverses to one another in the following sense. We will write the identity and G is the identity for some G, okay, where the equality is an equality between, well, you have to work out what the type should be for these equalities to make sense, okay? This will be the idea. So there will be an idea that we want to say not only are there proofs back and forth, but I can say that these proofs are mutually inverse in some way. And that induces a notion of equivalence of types. Okay? So that's one of the central ideas that we're going to be developing. And certain theorems and even certain axioms in homotopy type theory are expressed as equivalences between types, which are stronger than biconditionals. Okay? So that's I just want to give you a flavor to foreshadow a little bit, like the kind of thing we're going to be doing. And so this is very common. Now, another thing that will happen is we are going to eventually talk about what is the relationship between an equivalence and an equality in general. And I'll just for the sake of bringing it up, I will mention it right now, just so you can kind of get your bearings. We will eventually have something called the Univalence Axiom, which says that with respect to a universe, if A and B are equivalent in a universe, you would kind of like to say, well, at least if and only if A and B are equal in that universe. So equal types are ones which are equivalent in the sense that I'm sketching here, not very precisely, but I will make more precise. But it's actually even stronger than that. The Univalence Axiom not only says that, but it says, in fact, there's an equivalence between these things. Okay? So that the space of equivalences, this is a type. So you see, the interesting thing is this is going to be a big type, because what does it mean for these things to be equivalent? Well, it's a sigma type that says there's an F here, and there's a G here, and some additional data, which I will get back to later. So it's a type. You see, statements like A and B are equivalent is a type because we have propositions as types. So it's a space of a certain form, and we want to relate it to some other space of a certain form, namely the space of, well, what will turn out to be paths in the universe, or are identifications in the universe, or proofs of their equality. So I'm foreshadowing because I'm using a lot of ideas that I haven't fully developed yet, but I thought it would be kind of nice to say, you know, this is where I'm heading. So there's going to be some ideas about this. And this is a characteristic feature, okay, of homotopy type theory, is this axiom that Voevodsky proposed, saying that we should take equivalent types to be equal. Okay, before you can grasp the meaning of that, I really now have to develop the idea of what is the identity type, and then we'll come back to a better way of, you'll be able to appreciate what is being said here a little bit more. But I thought it might be nice just to tell you where I'm going. So I'm going to start talking about the identity type, but before I do that, I want to fix a picture in your mind. Okay, I'm going to fix a picture. Is this okay? Everyone got this? I'm going to fix a picture in your mind, which will be helpful in a little while. So it'll be nice to plant the picture right now. I want to look at sort of what we'll call what you might call two views of what is a family of types. Okay, so the one that we've been working with says that a family of types is essentially a mapping from some type A into a universe U. Because remember we said given X in A, so family, let's call that F, okay? So we can say that F of X, that is F has an X in it, is a... What? I can't hear you.
Too hard to read.
Oh, well, what pen do you want me to use? I have a red pen. That doesn't look too good. That's a red pen. That's a green pen. What do you want me to do? All right, it's green. Okay, so we have two views of a family. Let's see if this helps. Is this more readable? Okay. Like this, which is just, I'm using the function space. It's a little, you can write it like that. So what we said in the beginning is that a family is a type. So we rendered a type as being a member of the universe U, parameterized by a variable ranging over some other type. So it's an A-indexed family of types, or really an A-indexed family of members of U, which we're going to consider to be types. So we can think of a view as a family, we can view a family as such a function or a mapping like this. So it leads to the following kind of picture, all right? The picture is you've got A here, and A has got some points in it. Let's call them A1 and A2, all right? Just to pick out two that would be of interest. Of course, it might not even have any, but let's just put it a couple of points in there. And then the picture you kind of have is that A1 gets sent to its own balloon, which is sort of F of A1, and A2 gets sent to its own balloon, which is F of A2. And this is also a type, right? Written like that, okay? So that's the kind of picture you have when you are thinking of a family as a function. You can sort of think of it as a function from a type into a universe of types. This is why a universe is very important, because it gives me a way of specifying the range. So the reason I did it is it gives me a way to specify the range of a family in order to think of it as a function. If I want to think of a family as a function, I need to have it be going somewhere, which has to be a type. And so the place that it's going is a universe of types. Okay? So the idea is that you can say this business here, if I draw a box, this is the kind of thinking you're going to have to get used to. These individual balloons, if you just black them out and shrink them down, are points in U. Okay? Right? Those individual balloons, F of A1 and F of A2, are merely points in U. Okay? But when we zoom in, because of what U is, when we zoom in on those points, they are themselves classifiers, okay, of other points. They are types. Okay, so this is what I would say, particularly the path I've taken here that I've explained to you. This is what I would say is, probably your basic intuition about what is a family of types. But there is another way to think about it, okay, which is by something called the total space of the family. We can associate with this function f a type exist x in a f of x. And this is called the total space. And you'll see why in a second, why I think of that as why that's the right terminology. So if you remember, the big sigma is a sum, okay? So this is a sum of all of these f of a1s and f of a2s and whatever all the f of a's are. It's the sum of all of the f of a's where a ranges over a. So what I'm thinking of is I'm forming a type that consists, see, U is pretty big, and there might be like a balloon over here that is not in the image of F. There's no reason to think that it's onto in any way, right? U is a universe of types, and maybe here is the type nat, and quite possibly for this particular F, it doesn't land on nat. There's no way. I mean, it could very well be, right? It's just the idea that it's not necessarily onto. But what's happening here is I'm gluing together all the balloons that actually arise and forming a single space. So you can think of these things, and there's a picture that I'm going to draw. So that's called the total space of the family. And one of the things that this is equipped with is a projection called first we talked of that goes down to A, which is called a display map. Okay? And what that thing is doing is it's telling us, if you take this big sum, like you might be tempted to think of this as a union, but it's not a union. I'm not unioning up. So you can, like I mentioned to one student yesterday, one thing that is important is to jettison your set theoretic view of things, okay? You got to get rid of that, okay? Because it's not helpful, okay? It's only misleading. So this is not a union, but you could say it's a disjoint union, or really properly it's a sum. It's a big sum. So the idea is that what are the elements of that type, just so we know, right? The elements of that type are pairs consisting of an element A and A, together with, let's call it B, I don't know, which is in F of A. And notice the dependency. Where B lives depends on which summand you're in. So I will have this element, and I will have this element will be in the total space, but this element in the total space will be marked as being in A1, and this element in the total space will be marked as being in A2, so that I know where it came from. And the display map is recovering that information, because what the display map is going to do is send that to A. It's going to say, please display for me what element of the index space, the base space of the family, as it's sometimes called, is it over? So I write the map vertically like that. And it leads to the following picture, which I find very useful, and we're going to find useful very shortly, and when I start talking more about equality, is if we think of the total space, this is my total space being written here. So this is that big sum, okay, sigma, which I write here. And if we think of A as being down here, so that we have this mapping first of A, and then just like we had over here, let us focus on two, just for the sake of discussion, two different points within A. So we have two different elements of A, let's say, just for the sake of discussion, okay? The way to depict this, to depict what is going on here that is very, very visually helpful, is to think of this as, think of the total space as having vertical segments. My drawing skills are not the best, so let me broaden out A and make it look a little wider. So I will put A2 here and I will put A1 here. And this line here is to be thought of as, this is F of A1, and this line here is to be thought of as F of A2. Because what we're doing is we're saying everything in this line is sent down to A1. That's why I drew it like that. And everything in this line is being sent down to A2. In other words, we can organize visually the total space in such a way all the things that are labeled A1 are put on top of each other in this kind of stack or something. And all the ones that are labeled A2 are put on top of each other like that in sort of a stack. And then the idea is that this line, okay, lives over A1. So this is called, the terminology is the, depending on whether you're British or not, it's either fiber or the other way around, over the fiber of F over A1. And this is the fiber over A2. Okay? So that's the idea. Okay? So This is a picture we're going to come back to. I'm going to need this picture fairly often. But it's just kind of useful visually to say when I have a family of types, one way to think about it is all this stuff gets drawn out into a long line and it's written vertically like this. This balloon just is written out in a long line. There's nothing geometric going on. It's just a way of thinking, a way of visualizing it. So all of this thing gets all, these are all the elements of f of a1 written all above each other. These are all the elements of f of a2 written all above each other. And they have the characteristic that they're sent to a1 by the display map. So first sends us down here and first sends us down here. Another way to think about it is that this line is the pre-image. This is something like first inverse of A1, whatever I mean by that, okay? And I'm going to say in a little while what I mean by that. And this can be thought of as the pre-image of A2. That is, it's all the things that first sends to A1. And this is all the things in the total space that first sends to A2. Okay? That's another way of thinking about it. Okay? So it's sort of like the total space organizes all those inverse images and puts them in like some nice organization for you. Okay? That's a way of thinking about it. Yes?
So in a way, those two views are kind of dual. So those two different views are kind of dual. In one you have a function, and the other one you have a problem. So you're just reversing the...
I didn't hear that. What? Say again?
So those two views
Yes.
are dual in a sense, because you're just reversing the...
Oh, you are reversing there. So the question was, those two views are dual in a sense, and that's actually quite true. The thing that's kind of funny about it is that here A plays a role as being in the domain, and here the role that A plays is in the codomain. And so this is quite true, okay? And you can go back and forth between these two representations. And I'm not going to deal with that right now. But it happens a lot that we write it like this. So when people are thinking this way, very often, just as a matter of terminology, very often people will say, well, this is what we'll call a family, and this we will call a fibration. Because it creates these fibers, okay, it's this fibered view of what's going on with the family, okay? Now, there's something very important about a fibration, which I'm going to get to in a minute, which has to do with the behavior when there is an identification between A1 and A2 in either case. There's going to be an interesting question comes up, all right? But let me just, again, I decided I struggled mightily yesterday in preparing my lectures. If I get too technical, you know, I'm trying to walk a line between all technical details, which will put everyone to sleep, and being just BSing, and I don't want to do that either. So I wanted to like somehow find the right path here so you get the main ideas. So let's see how successful I am. So there's going to be an interesting question, which will come up very shortly in this lecture, is what to say when there is an identification between A1 and A2, when those are to be considered equal. If you take this view that it's a function from A into U, you might very well anticipate that there must therefore be some sort of identification between these two balloons. And that identification would naturally be thought of as some kind of an equivalence between them. Okay, that these two guys that we've written here should be equivalent, right? That those two balloons, if A1 is to be regarded as the same as A2, I've identified them, then the balloon associated with A1 should in some sense be the same as the balloon associated with A2. But now comes the important point. It's true that U is a type, and these balloons, if you just, zoom out far enough, if from 10,000 feet, they're just points in U. So you might say an identification between A1 and A2 induces an identification between the point f of A1 and the point f of A2, and that is true. But the point is that these things have structure. They're not just points, abstract points that have no internal structure. They're not somehow little atoms. they themselves have structure. So what it means for them to be identified should mean that in some sense there's an equivalence between them. That is, there's mappings that go back and forth that are mutually inverse to each other that tell us, so to say, point by point, everything here corresponds to something here. Okay, and vice versa in a completely systematic way. If any of you have ever studied category theory, what I'm hinting at is the notion of an equivalence of a category, equivalence of categories. An equivalence of categories is an isomorphism up to isomorphism. Okay? If you just write down the notion of a category as an algebraic structure, something that looks kind of like some fancy version of a group or a monoid or something, like just an algebraic structure, you would naturally say, oh, I've studied algebra, so let's look at the homomorphisms between them. Those are called functors. And then we say homomorphisms that are invertible would be called isomorphisms. And that notion is not very useful in category theory. And the reason is because a category is not somehow just a point thing that we're not analyzing. It itself has structure. And so what we want to do is we want to weaken the notion of when these two balloons are equal to account for that structure by saying that that equality should be an equivalence. So in category theory, there's a distinction between an isomorphism of categories, which is rarely is useful as far as I know. Maybe some experts know, but it seems to me rarely useful. The thing that is extremely often useful is the notion of an equivalence of categories, which is an isomorphism up to isomorphism. So we'll get back to that in a minute, okay? So a similar thing has to happen. If this is the kind of picture we're going to have here, a similar thing has to happen on this side, okay? There has to be some way of saying that if I think of the family as a fibration, so I have a projection, a display map from the total space to the base space, and if there is some kind of identification between these elements of A1 and A2, then there should be some kind of lifting property, okay, that lifts the identification here up to here. So let me erase the little annotations to make some room for myself, okay? All right, so remember that the fibers, these vertical slices through the total space, those fibers are to be thought of as consisting of the points of f of A1 and the points of f of A2. They're all lined up there, okay? That's the way to think about it, right? So you might think something like this. If A1 is identified with A2, what I want to do is I want to take this thing, which I will eventually call a path P, and I want to lift that path up to the fibers in such a way that everything over here somehow corresponds to everything over here in a nice systematic invertible way. Okay? That's what I'm going to get at. And this is called the path lifting property. Okay? And in fact, in axiomatic treatments of homotopy theory, the definition of a fibration is a map that satisfies this path lifting property. That's just the way it's done. Okay? I'm motivating it here from the point of view of type theory. So this is what's happening. So there should be some correlate, which is usually called P lower star, which somehow says something about what happens over here and over here. Now the way that's going to work, I'm going to show you how this is going to work, and there's going to be some subtleties to this picture, but right now let's set that in our mind as some kind of motivation, okay, for what is going on. Okay, so we'll get to all the details very shortly. Okay, so these pictures are good to fix in your mind because it'll help me motivate what I want to do. All right, so now let's just let that settle. I wanted to sort of plant it, okay, early enough, okay, so that when I come back to it later, you'll say, oh yes, I recognize that, so that's good. And by the way, the role of the univalence axiom, I should have said, is exactly to say that thinking of these as points being identified is exactly the same as saying that thought of as balloons, they're equivalent. That's the idea of the univalence axiom. Okay? So it's the nature of identifications in a universe. That's what we're going to get at. Okay, so there it is. Okay, so that's like where we're heading. So that's like the big overview of the next set of technical details. Now I have to like do some more technically involved work. So let's go back now to considering the nature of the identity type. So as I mentioned, historically, there have been two notions of what to do about the identity type. There's the so-called extensional identity, okay, which has, so what they share, okay, the type theories, regardless of how you look at it, they share the principle that if A is in A, then reflexivity in A at A is an identification between A and itself. Or, as I will very soon start writing, I'll just say A equals A. You're going to have to get used to something to which you tend to have a very deeply baked in propositional attitude. You must always remember that in type theory, anything toward which you have the attitude of a proposition is really a type that classifies some terms. That's the main hump you've got to get over, okay? Because that's the thing, as I say, I'm addressing, I think, the majority view. That's the thing that is distinctive about the type theoretic view. So I'll write equality, and you're going to get tripped up because you're going to start thinking of this like you've always done in your whole life. And it's a generalization of that. That's the best way to think about it. It's a generalization. So this is the equality introduction. Okay? So we're going to share that. There's going to be other forms of equality introduction. Unfortunately, I erased it. Like the Univalence Axiom will be another form of equality introduction. So this is the one, equality introduction for reflexivity. So all the type theories agree that amongst the identifications one could have, reflexivity, we all agree, is going to exist.